Alrighty, so we're going to do some practice with the first order homogeneous constant coefficient linear ODEs, which is basically ODEs that you can convert into having characteristic equations. So they're like AY double prime plus BY prime plus Y equals 0 because it's homogeneous. In other videos, we've talked about how there's basically three options that you can have two real solutions. You can have one repeated real solution, and you can have two complex solutions. And based on what kind of solutions you have to the characteristic equation, it should be something like AR squared plus BR plus C equals 0. Depending on which kinds of solutions you have to that, then you know what kind of solution to guess. So if you have absolutely no idea what I'm talking about, then you want to go find a video that'll help you with that, because we're assuming you've already got that, and we're just kind of practicing the skills to make sure they're settled. So I'm going to give you 3. Actually, I'm going to give you 4. So here are the 4 problems for you to take a look at. And I'm just going to say that the 4th one, you really want to notice that these initial conditions are not actually initial at 0. They're initialized at x equals 1. And so there's actually a trick to doing that. But go ahead and solve it the way you think you should. And if you can come up with a trick, great. If not, make sure you go ahead and watch through and see exactly what we do to solve that. So go ahead. Seriously, pause the video, go work these out on your own, because if you're just staring at you working them out, you're not really getting anything out of it. You really need to pause it, you really need to go think about it, and make sure if you get stuck, go look at your notes, go figure out what's going on, and then come back and be like, oh yeah, I got it. And if you didn't, then pause it and try the rest of them. Don't just be like, I didn't get the first one, I guess I'll just watch all the video. Just if you didn't get the first one, then try the second one, learning what you remembered, and just keep going from there. Okay, so we'll assume that happened. Now looking at a constant coefficient ODE like this, the first thing you should be able to do is go pull off the characteristic equation just by looking at it. So now I've got this. I can factor this. I've got r minus 5 squared is equal to 0. Therefore, r is equal to 5, but it has a multiplicity of 2. That means that the general form of the equation is a e to the 5x plus bx e to the 5x. If you forgot the second x, you really missed something. Now, in order to apply my initial conditions, I can apply the one at y at 0, but I'm not going to be able to apply the one at the derivative unless I actually take the derivative. So this is what's going to feel like a whole lot of what you're doing, is taking lots of derivatives and finding initial conditions. So we got to make sure we do this right. It's b e to the 5x plus 5b e to the 5bx e to the 5x. Like that, because I took the derivative of the x, and that's good, and I took the derivative of that. Okay, so that's good. So now I actually want to apply the initial condition. So y at 0, that's 3, so I'm looking at this guy right here, is equal to a times e to the 0 plus b times 0 times e to the 0. So that's a plus 0 is a, so that means a is equal to 3. If I apply y prime at 0, that's the other one. I know that's equal to 6, so I've got a, or 5a, oops, sorry, not da-da-da. I have 5a, I'm just going to write a for a minute, times e to the 0, plus b times e to the 0, plus 5b times 0, so that's going away. I know that a is equal to 3, so I can go ahead and plug that in as well. So I have 6 is equal to 15 times 1 plus b. So that means that b is equal to negative 9. And so I can say, well, the full solution to this problem is that y is equal to 3 e to the 5x minus 9 x e to the 5x. And it's all beautiful and happy, and that's my full solution. So that's really all we're doing on these, is just lots of practice. All right, so now let's try this one. Again, just reading off the characteristic equation, r squared plus 6r plus 5 is equal to 0. So r plus 5, r plus 1, r equals 5, or negative 5, or negative 1, like that. So that means that I guess a solution in the form y is equal to a e to the negative 5x plus b e to the negative x. Again, to apply the initial conditions, I'm going to need the derivative, so negative 5a e to the negative 5x. This one's a little bit easier, minus b e to the minus x. So if I apply the first initial condition, I get 3 is equal to a plus b. If I apply the second initial condition, I get negative 1 is equal to negative 5a minus b, like that. And so, because I can algebra, I can solve that. So I've got 2 is equal to negative 4a, so a is equal to negative 2, which means that, 3, negative 2 plus b, so b is equal to 5. Oh, wait, no, that's not right. Math is apparently harder than I thought. I got all excited. A is equal to negative 1/2. That was goofy. All right, 3 is equal to negative 1/2 plus b, 6/2, 5, no, 7/2. Now I'm all paranoid. So b is equal to 7/2. So I have, again, it was in the form with the a. I'll just zoom out a little bit. Oops, other way. So I've got that y is equal to, again, reading from up here with my a and my b. I'm just going to plug it in. So I have negative 1/2 e to the negative 5x, and then plus 7/2 e to the negative x, and that's my full solution there. Getting there. Making sense? Once you know what you're doing, it's super easy. Now by super easy, I mean easy compared to other stuff that's not easy. All right, so now we've got r squared plus 4r plus 13. That's not going to factor, so I can plug it into my quadratic equation. 16 minus whatever 13 times 4 is, 52 over 2a, and 52 minus 16 is some other number. 36. Okay, there we go. Minus 4 plus or minus negative 36 over 2. Plus or minus 6i, 2. So negative 2 plus or minus 3i. And again, I know my standard form. It's e to the minus 2x, a cosine 3x, plus b sine 3x. Like that. To apply my initial condition, I'm going to need to be able to take the derivative of it. And that's going to be more fun than usual. Okay, so if I'm going to take the derivative of it, come here, girl. Sorry. Whenever I need to take the derivative of it, I'm going to take the derivative of the outside. Negative 2, e to the negative 2x times everything in the inside stays the same. And then I'm going to add the derivative of the inside. So that'll be 3a negative sine 3x plus 3b. Thank goodness I don't have to do this twice. Cosine 3x. Like that. Looks relatively straightforward. Okay. Now I'm going to actually apply those initial conditions. My initial condition said that y at 0 was equal to 2. So I have e to the 0, a cosine of 0, plus b sine of 0. Sine of 0 is 0. Oops, I meant to do that in another color. Sine of 0 is 0. Cosine of 0 is 1. This is 1. So that means I've got that 2 is equal to a. So that's nice. And I know that y prime at 0 was defined as, or set as, negative 3. So I've got negative 3 is equal to negative 2 times e to the 0, which is 1, and then a cosine 0 plus b sine 0 plus 1, negative 3a sine 0 plus 3b cosine 0. Cosine of 0 is 1. Sine of 0 is 0, sine of 0 is 0, cosine of 0 is 1. Keep going, just kind of power through, do some math. Minus 2 times a plus 1 times 3b. I know what a is. And I just keep doing math. So b is 1/3. So I'm able to write my solution. If I zoom out, I can see what's, other way. I can see what's going on. Maybe if I can still see my initial thing, I'll just write it over here. So I've got that y is equal to e to the negative 2x. The a was 2, cosine 3x, and then the b was 1/3 times sine, I'm going off the page, of 3x. And that would then be my full solution that meets my initial condition. So that would be kind of what I was looking for. Kind of makes sense? Great. All right, I promised you one more, and I said the last one was a little bit tricky or had a trick to it. So I'm going to go ahead and solve it I didn't think of the trick way, and then we'll solve it the tricky way, and then you can just be like, wow, I'm going to do it the tricky way in the future. Okay, so I'm just going to do r squared plus 3r plus 2 equals 0, r plus 2, r plus 1. So r is equal to negative 2 or negative 1. So my solution is in the form a e to the negative 2x and b e to the negative x. I'm going to apply my initial condition at 1. Now the only thing that's annoying about this is that it's just going to look less pretty for a little bit. So it's negative 1 is equal to a e to the negative 2 plus b e to the negative 1. All right, I'm also going to need my derivative. So the derivative is negative 2a e to the negative 2x minus b e to the negative x. So y prime at 1 is 4 equals negative 2a e to the negative 2 minus b e to the negative 1. And I'm going to math my way through this. Those are going to cancel. I've got negative a e to the negative 2, so that's, I'll just write it out because I'm afraid I'm going to do something stupid because this is not the best way to solve this problem. So I have a is equal to negative 3e squared, okay? And I know from this that negative 1 is equal to a, which is negative 3e squared, times e to the negative 2 plus b over e. These are going to cancel out, and I end up with negative 1 equals negative 3, negative 1 equals negative 3 plus b over e, plus 3 to both sides, 2 equals b over e, so b equals 2e. So it's not really going to matter in the end, it's just kind of a neat little trick, but I'll show you what it is. So I'm going to get the same answer both ways, which is why I'm solving it this way. B is 2e, e to the negative x. Okay, so that's my solution, like that. Now, I'm going to show you another way to do it. Okay, so remember a long time ago, whenever we were looking at these problems, we pretended, or we assumed, so I'm going to say before we guessed y is equal to e to the rx. And that was fine and lovely. But what if instead we guessed we actually guess y is equal to e to the r x minus 1? You say, well, why'd you pick 1? I picked 1 because my initial condition was at 1, and if I put in a 1, then this is going to go to 0, and the whole thing is going to go to 0, and it'll be kind of pretty. Now, if I do that, I'm going to end up with e to the rx minus r, which is e to the minus r e to the rx. Now, this is just a constant outside what we normally had. So whenever we plugged in everything, we ended up with something that looked like ar squared plus br plus c, and we had an e to the rx out front. You're like, I have no idea what you're talking about. Well, we did this whenever we derived stuff. When we originally derived what the 3 options were, so we talked there were going to be 3 options, and we started off by guessing e to the rx. Now I'm just saying, what if instead of guessing e to the rx, we had guessed e to the rx minus some other number? Well, basically all we'd end up with is an extra e to the minus r out front. Because this is just a constant that would have ended up getting multiplied, and take the derivative of the constant, whenever it's within a function, that constant remains within the set. And because it's non-zero, it just would come out here. So basically, we'd still end up with the exact same characteristic equation. And the only difference is that whenever we plug things in, we'd have that e to the r. So say we had the solution, which was a linear combination of the two options. So it would be e to the r1, x minus 1, and e to the r2. So these would be our two solutions. We'll just use this as an example. Well, whenever I would do this, I could have e to the negative r1, e to the r1x, and b e to the negative r2, e to the r2x. So basically this is still just a boring old constant, and I could still just call that a, e1 to the rx, and b, e to the r2x. And it doesn't change anything, it just changes the constants. So basically what I'm saying is, what is she doing here? Basically what I'm saying is, we got our two solutions. We had r equals 1 and r equals negative 2. So I'm saying instead of doing this, where we had a e to the negative 2x and b e to the negative x, that instead we could just as easily guess a e to the negative x minus 1 and e to the negative 2, well, let me put them in the other order because that's how I did them, is I could do negative 2 to the x minus 1 instead of times x, and b to negative 1 times x minus 1. Because all that I would be doing is pulling that other term, and it would get globbed into the constant anyway. Why would I do this? Just because it makes my life a little bit easier. You're like, it doesn't seem like it. Well, watch. This is just kind of cool. And this makes a difference the more complicated these get. So this is, especially when you got sines and cosines, this might be a whole lot better to mess with. So let's see. If I take the derivative, I've got negative 2 a e to the negative 2 x minus 1 minus b e to the minus x minus 1. Now whenever I apply my initial conditions, I have y at 1, which was negative 1. But now whenever I plug this in, I get a to e to the minus 2 times 0, which is just going to go to 1. And then b, e again to the minus 0. So what I end up is negative 1 is equal to a plus b. Now you see how this looks a little bit better? I don't have those stupid e's in there. Same thing here. Y prime at 1 we said was equal to 4. So I have negative 2a, e to the 0 is 1, minus b, e to the 0 is, whatever you call it, 1. So I have 4 is equal to negative 2a minus b. Now again, this is a lot less heavy math to do for me. It just takes less effort, but these numbers should look familiar-ish, except I can't add. Oh no, I can add, I just can't do that. All right, so a is equal to negative 3. So that means that negative 3 plus b, add 3 to both sides, gives me 2. So that means that my options are negative 3 and 2, or my constants are negative 3 and 2. So I've got negative 3, e to the minus 2, x minus 1, plus 2, e to the negative x minus 1. You're like, no. Okay, hold on. You totally messed this up because you said that they were going to be the same, and they're clearly not the same. So let's go see what we had before, just so there's no trickery. All right, so we had this before. I'm going to make a copy of it, and we're going to take it down here. You can't see all of what I have, but it's coming down here. So last time I did this, I got that. Okay, so basically I'm going to show you that these two are the exact same answer. So this is what I got with my trick. Tricky. This is the non-tricky way. Okay, so I'm actually going to argue that the tricky way gives you a prettier answer and makes something that's a little bit more obvious about what's going on, because you can see that there is a significant inflection point or something interesting is going on at x equals 1. But let me show you that this is the same. So I have that y is equal to negative 3 e to the negative 2x plus 2, 2 e to the negative x plus 1, negative 3, e to the, I'm going to pull out a minus 2, I end up with x minus 1, and I'm going to pull out a negative 1, and I end up with x minus 1. So you actually see I got the same answer both ways, but I'm going to argue that the trick answer is not just trickier, but it's prettier, and it's easier to understand, it's more clear, the constants are much nicer, it's a lot less intimidating, a lot less scary. So you still get the same answer both ways, are equivalent. It's just that you can adjust that initial, or you can adjust the exponents to correlate better with your initial conditions, and you'll get a much nicer answer.